Hi guys, welcome to another Learn Electronics Repair video. I have on the workbench today quite a large audio amplifier, a Power Amp PA. It's I believe a 3 kilowatt one, so it's quite high powered. And this is the sort of thing that they use in clubs and concerts and on this island for the carnivals. So I need to repair this amplifier, and I thought it would be a good opportunity because of some of the comments I've had recently to other videos. I know that a lot of you guys would like to see a video all you need to know about audio amplifiers to fix stuff. And you know what guys, that's a really big subject, and I'm not quite sure at the moment I can actually put all that together in one. But what I thought I would do is make this video, which is a beginner's guide to audio amplifier repair. This is to get you started. So first of all, let's have a look at the amplifier we have, a quick look around it. Then let's have a look at the theory of amplifier design, the types of amplifier you're commonly likely to find. No mathematics, just the difference between the common types of amplifier you're going to find, audio amplifier. And when we've done that, let's do a practical. So we're going to attempt to repair this amplifier. I hope you're looking forward to this, so let's get started. I have an amplifier here. This thing's so heavy. Oh, God, they picked the thing up. It must weigh about 25-30 kilos. I mean, Hill DX3000, I think it's a 3 kilowatt power amplifier. And if you guys wonder, I mean, it's like 1500 watts per channel. If you look at these little amplifiers they make these days, and they say like 1500 watts per channel, why do you think it takes this much weight in electronics to make an amplifier that can deliver that power? Yeah, God, it's heavy. I think the guy this belongs to, he has a company, so they do PA systems and such like. He does carnivals. You know, have these carnivals here in the street with big articulated wagons coming down, trucks with dance floors on them, and you know, PA systems so powerful they actually shake the ground. And that's, I think, what this comes from. So I've taken the end off. You see, there's lots of transistors in here. 2, 4, 6, 8, 10 down each side, and obviously 2 channels. And this is, I think, it's actually the rear side of this. So you see the transformer, the electrolytic capacitors in here, 18,000 microfarad, 125 volts each of these, so you don't want to be touching them if you're worried about capacitors with charging, that's for sure. And that actually means that when this is powered up, if there's going to be a lot of voltage in this, so although you think, well, it's an amplifier, it's got a transformer, doesn't mean it's not necessarily hazardous to work on in some respects. Yeah, this has been added on here. This is something I actually did this a few years ago. So there was a thermal trip, or like a kind of like a fuse trip on the back that was faulty. And let's see, it's on here somewhere. Can't quite see it. I know when I looked at this before, it was working then. So there was a trip in here somewhere that was faulty, and I couldn't get one of a physical size to replace it. So I actually wired one inside here. You can see this thing here does the job. I think, yes, I remember now. So let's have a look on the front of this. The on-off switch, which I can hardly get into the shot. The weight of this damn thing. The on-off switch, in fact, we had 2 poles, and one side of it was like a thermal trip that would trip out, and it was open circuit, so I wired this in. So we still have a thermal trip, and I mounted this here. So that's actually on the main power coming in. Yeah, it comes through this and then goes off down to the transformer. I've turned the amplifier over so you can have a look at the other side. There was 2 metal plates here which I've removed. And we can see the other side of the amplifier modules now. So, I mean, straight away I can see some couple of transformers, a couple of relays I notice. And I'm not sure how easily I can actually get these amplifier modules out of here, but we can see a positive and negative supply coming in. There's two of them on each of the amplifier modules. This is probably ground, I'm guessing, so there'll be the plus and the minus supply. We can see this on those capacitors on the other side as well. I'll show you again in a moment. So this is basically what we have to work on with this. Yes, we have on this side, we can see again, we can see the red and the black. And then I'm guessing that these are all connected together, these parts, these capacitors. We can just have a look. I'm just going to use my fluke meter for a moment because somebody said that I needed to clean my multimeter. So I actually did the most sensible thing, which was to take the casing off it, this plastic, take it home and ask the wife to wash it. That worked quite well. So let's just have a look. So I'm pretty much assuming that both ends of these are actually connected together. Yep, that looks like it is. And that looks like it is, yeah. And then we'll have the supply, so we can just check. There's no short circuits on here. That's a good thing. Let's go to the other ones. This is the negative end. We'll go to the other polarity just to check it. Yeah, you can see the capacitors charging up. Okay. Yep. So there's no short circuits on it. That's nice to see. Also, just looking down here, I can see two bridge rectifiers. This one and this one. This one has the red wires going to it. Yeah, one red, one black. So this bridge rectifier is effectively across the two ends of here. And this ground, this will be a center tap on the transformer. And the same here, we have another bridge rectifier, which is the red and black here. And again, these will go to a center tap on the transformer. And down in the middle is a third bridge rectifier, which comes from two orange wires here. And that has then some thin black and red wires on. So I'm assuming this is like a low voltage supply to the circuitry, not the main amplifier section, but the sort of the components before that, like the preamplifier, if you like. So that's what we appear to have. But let's have a look first. So I'll draw this out what we have, and while we're doing that, let's have a look at amplifier design in general and amplifier repair in general. So we can make this a beginner's guide to audio amplifier repair. I doubt it's possible to do an all you need to know, it's such a big topic, but let's get the basics first. Let's get a good grounding with this, and then we can start repairing amplifiers. Probably the first thing you need to know about audio amplifiers is they are not all the same. In the same way that power supplies come in different types, you get linear power supplies, switch mode power supplies, or even something like an ATX power supply. If you saw the recent video I made, there's a number of common designs or topologies, and that's also true of audio amplifiers. With amplifiers, these designs are called classes. So you may have seen this. You get things like a class A amplifier, a class D amplifier, and so on. This class has nothing to do with the actual quality of the amplifier. It's not a case that a class A amplifier has better performance or better sound quality than a class B, and so on. These classes are the topology, the design of the amplifier. Amplifier classes go from A, B, C, D, E, F, and so on. But not all of these designs or topologies or classes are actually audio amplifiers. There are some classes that are RF, radio frequency amplifiers. The classes that you will find with audio amplifiers are these ones. You have class A, you have class B, you have class AB, which is basically a combination of these two, a kind of a halfway house. Then you have class D, you have class G, and you have class H. So these are the different topologies, the types of audio amplifiers that you're likely to come across if you're doing repair work. So of course you're going to want to know what is the difference between all these classes. So let's have a look at each one in turn, and I'll explain briefly how each one works. And then after we've been through this theory, we can look at our amplifier, see which class ours is, and then we can get on with the repair. The class A amplifier is the most simple. I'll draw you a basic circuit. This is using a MOSFET, but you can also do this with bipolar transistors as well. But there's one principle that is true of all class A amplifiers. So with a MOSFET, we'll have a 12 volt supply, and I'll just draw you a circuit. So we have a MOSFET to ground. Okay, this is the gate of the MOSFET, and we have then coming in to a capacitor. This is your audio in. Okay, and we have audio other side down to ground. So this is where you feed your audio in. You have your MOSFET, and then you need a couple of resistors. So what you basically need to do, we'll put a variable resistor to ground here, another resistor to the gate, and this sets the bias, which I'll just explain in a moment. Your output comes from here to a capacitor to your output. So this is effectively where you would connect your speaker. Okay. The idea of this bias is that you have to set the gate voltage so that the voltage at this point is half of the supply voltage. So if you have a supply voltage of 12 volts, by adjusting this resistor, you're effectively adjusting the voltage on the gate. Okay, and you adjust that so that the voltage here is 6 volts. The idea of the other resistor here, by the way, is that even if you put the variable resistor all the way to one end, it can't connect directly. There's always some resistance between the drain and the gate. Drain, gate, source. So this is quite a simple circuit. You adjust this so you've got 6 volts here. Okay. When you feed an audio signal in, AC, the capacitor lets the AC come through. The DC is blocked, so this will not affect the DC voltage here. So on the positive half cycle, you increase the voltage on the gate, the FET turns on more, and the voltage on the drain drops down towards 0. Okay. When this goes negative to the negative half cycle, you decrease the voltage on the gate, the FET turns a bit more off, and the voltage on the drain goes up towards supply. And if you have the correct amplitude coming in here, you can effectively change the voltage here from 6 up to 12 or down to 0. So effectively your output here is about 6 volts peak to peak. Okay. This capacitor here is to stop DC coming through your speaker all the time, because your speaker diaphragm naturally sits in the middle, okay, the coil in your speaker. So your speaker has a coil inside it, which effectively is moving in a magnet. So you have a magnet around this coil, and the coil is attached to the speaker cone, okay. So as you pass current through here, one direction or the other, it magnetizes in one direction or the other, and that's what actually makes the speaker cone move in and out. So that's how the circuit actually works. So the end of the coil obviously comes to here. So you don't want a DC voltage going through the speaker, because the speaker cone would move to one end and stop there effectively when there was 6 volts on here. That means that it can't move further that way, so it can't reproduce the sound correctly. And anyway, having a DC voltage flowing through your speaker coil is not a good thing. So that's how this circuit works, basically. The advantage of it's very, very cheap, if you like to make, is a very simple circuit. The disadvantage is that this MOSFET is effectively always passing current. So even when there's no audio coming in, this is passing current. The voltage here is 6 volts, means there must be a voltage drop across this resistor, and the only way there can be a voltage drop across this resistor is if current's flowing through it. So the current flows through the resistor and through the FET. And that's the disadvantage of this design. These things are used in very low powered amplifiers, maybe little transistor radios and such like. But even so, it's not a particularly good design, because even if you had no sound, it's draining from the battery. Yeah, it's very inefficient. The efficiency of this circuit, that's the wattage that's turned into sound, rather than the wattage that's just used to pass through this FET all the time, is about 25%. You can find similar circuits with bipolar transistors and more complicated ones with multiple stages, but the main thing you need to know about this one is that the output device is always passing current, even with no audio input. You can increase the output power of this by decreasing the value of this resistor, and if you like, putting more MOSFETs in parallel with each other, so they share the load, they share the current flowing through them. But because it's always passing current, it will just get hot, so you'll need large heat sinks, you'll need large power supplies because of this quiescent current all the time. So effectively, as well as making a powerful amplifier, you're also making a rather good foot warmer or room heater. Yeah. There is one other advantage to this design, and this is why these are often used for things like headphone amplifiers and such like, and some audio purists like these amplifiers. And this is because this device is effectively handling the entire waveform, the plus and minus. All 360 degrees of the waveform is being handled by this. Therefore, there's no distortion. You can get a very pure signal here. So you can have a small input coming in, a large input going out, and there's nothing really to add any distortion to the waveform. So this gives you, if you like, the purest audio quality. But due to the reasons I was saying, it's only really used for low power amplifiers. Now let's have a look at the Class B amplifier design. And the whole point of the Class B amplifier is to get around this problem of wasted power to improve the efficiency of the amplifier. So with a Class B amplifier, you have a positive and negative supply rail. We'll put 12 volts in again, okay, and we'll have a minus 12 volts. The way you get these, by the way, normally is in the power supply to have a transformer, very dodgy transformer. Okay, I'll draw the transformer, I'll draw the diodes. So you'd have a power supply, basically something like this, with a center tap on the transformer. So the center tap is basically halfway down the winding, it's just brought to a connection, and that's connected to ground. You then have capacitors here, and you also have capacitor here, or capacitors. And that basically gives you your positive and negative supply. So that's how you actually get the positive and negative supply. Now the amplifier, the Class B, effectively, I'll just show you here. So we know we have a plus, and it could be any voltage, I'll just use 12 volts, just to represent what we can do. Okay. With the amplifier itself, we're using NPN in a PNP transistor. Again, it could be MOSFETs, and it could be an N-type and P-type, or it could be transistors. I'll use transistors in this one. So these are your two transistors. This one is an NPN transistor, this is a PNP transistor. Put the base on here, and then from the base we have some bias resistors. So I'll just draw them in. Okay. And these resistors are set basically so each transistor is off. Okay, it sets the base voltage so it's not on, it's off, it's not doing anything. It's not passing any current. Okay, and the audio input comes here. We use 2 capacitors, and this is where we feed the audio in. Okay, and again the audio goes to ground, and our speaker actually goes from here, and the other end of the speaker is connected to ground. So this center point, this is effectively our ground. Now let's have a look how this works. We feed an AC waveform in here, the audio. Okay. When we're on the positive half cycle, through this capacitor, the AC increases the voltage on the base. Okay. It won't affect the DC voltage here because the capacitor only passes AC, not DC. So we increase the voltage on the base, and as that increases we turn the transistor on. So this transistor starts to conduct current down into the speaker to ground. Okay. So there's this voltage going up, the voltage on this emitter is also going up. Okay. Notice this doesn't invert the signal. Now on the other one, the other half cycle, the voltage eventually comes to 0 and goes below 0. And this being a PNP transistor, the base has to be below the voltage of the emitter to turn on. So this one now turns on. This one turns off because the voltage is below the emitter, and it's an NPN. The same as when this was conducting, the voltage here was above the emitter. Okay, so this handles the negative half cycle. This conducts, and it pulls the voltage on the emitter down towards minus 12 volts. So this conducts the negative half cycle and this conducts the positive half cycle. At no point are both the transistors conducting at the same time. So the advantage of this is that when there's no audio coming in, there's basically no output current. There's no output, it's not doing anything, yeah, apart from the little bit of current that flows through the resistors, of course. So that's how this circuit works, and you can see it's much more efficient than the Class A amplifier. Your output waveform now is basically going, assuming we have the correct level of input so we can fully drive this, the output voltage of this literally can go up to plus 12 or minus 12 on this point. So effectively we have about 12 volts peak to peak. And that's for the given voltage, that's the actual maximum output. The disadvantage of this circuit, this Class B amplifier, is that if you watch my video on transistors, all you need to know about transistors, you'll know that until the base voltage is about 0.6 volts above the emitter voltage, the transistor will not switch on. And the same with the PNP. The base has to be about 0.6 volts below the emitter before it will start to conduct. So in actual fact, you get a situation when the voltage audio waveform is near to 0, either side of 0, you get a point where this transistor is already switched off because the voltage here is now below 0.6, but this one isn't switched on yet because the voltage hasn't got to minus 0.6. And this is called crossover distortion. So what happens with your output waveform is effectively, as it goes through 0, it kind of distorts like so, yeah? And this is crossover distortion. At this point, one transistor is switched off, but the other one hasn't turned on yet. Another cause of distortion with this, these transistors are called complementary. So the NPN and the PNP transistor are selected to have matching characteristics, but no matter how well you select the transistors, it will never be exactly the same. So you may find that this one turns on at maybe 0.55 positive, but this one doesn't turn on till maybe 0.58 negative. So the distortion actually is not the same for either half phase. So that's the advantage, efficiency, and the disadvantage of Class B is crossover distortion. For this reason, you will not really find true Class B amplifiers these days. What you find is a halfway house between the two, and that is Class AB. The way the class AB works is based on this circuit. So what we do is we replace this resistor with a diode, okay? And we also replace this resistor with a diode, semiconductor diode. Now a diode, like a transistor junction, has a voltage drop across it. If you measure with your semiconductor analyzer, you can see about 0.6 volts. So what actually happens now with the two diodes in series is that this base will be about 1.2 volts higher than this base. 0.6 on that semiconductor junction and 0.6 on this one. The two added together is 1.2 volts. Okay. So now by selecting the value of the resistors, you can actually modify the performance of this so that both transistors are just turned on, but they just turned on in the quiescent state. Okay, the base voltages will be different because of this, and they'll be different by 1.2 volts. So we now have a situation where on the positive half cycle, this transistor was already just slightly turned on. So as the voltage goes positive, we don't have to wait till it reaches 0.7 of a volt. This starts to conduct straight away. And it continues to conduct until it reaches a 0 point again. At the 0 point, this one starts to conduct straight away because the base voltage, again, was set to a point where it was just turned on. So effectively by doing that, we get rid of the crossover distortion. Okay? And that is called class AB. This is a very, very efficient amplifier type. It can be scaled up easily so that you can have many transistors in parallel. We can do this sort of thing. So we can add more transistors in parallel on both halves. Okay. And the same obviously on the other half. So we can do this sort of thing with it. Okay. And we can make high powered amplifiers that don't generate so much heat as the class A. They're much more efficient, they're not wasting power. Because of the efficiency and the simple design of a class AB amplifier, almost all consumer equipment with amplifiers in are class AB, or at least they were until class D came out, which we'll talk about a little bit later. I'll just talk now, because it's just a good time to mention this, about this business of connecting lots of transistors in parallel. And this is true whether they're MOSFETs or whether they're bipolar transistors. When we have lots of transistors wired in parallel like this, so effectively they're all wired across each other, okay, to share the load, they're all driven from the same signal. But although the transistors can be matched, I mean, some amplifiers, you'll find that the transistors, the output transistors, were chosen specifically maybe from batches. So the amplifier manufacturer bought large quantities of transistors and then they batched them. So they put them in bins, they binned them, each bin having transistors of a very similar gain and a very similar base emitter voltage drop. But even by doing that, you can never absolutely match the transistors or MOSFETs. So what you normally find in this type of arrangement is that you have a small value resistor on the emitter of each transistor. Okay, this then goes to your loudspeaker to ground, and then the other side you'll have again small value resistors on the emitter of the PNP transistor going to -12 or whatever voltage we're using. Okay, so you will normally find, in fact I would say you will always find, in transistors where they have, in amplifiers where they have multiple transistors on the output stage, you will find these low value emitter resistors, and this is quite important when it comes to fault finding. Now let's talk about class G and class H amplifiers, because they're very closely related to the class AB amplifier. So we'll look again at the basic circuit that we just had. Speaker to ground, minus volts, plus volts, put our resistors and our diodes in. So there's our basic circuit, the same we just had. Okay, and our input through the capacitors. I'm sure you can draw one of these yourselves now, the basic topology of this. Okay, so how much power, how much wattage are these transistors dissipating? Yeah, that's the question. And here's the question: are they dissipating the most wattage when they're switched off, so no current is flowing through them? Are they dissipating the most wattage when they're switched fully on, so all the current is flowing through them? Or are they Are they dissipating the highest wattage when they're half on and half off? Which do you think it is, guys? Which do you think is the time when they dissipate the most wattage? Well, the answer is not when they're fully conducting, where they carry most current if we thought it was. And the reason for that is basically this: when the transistor is switched off, okay, when it's switched off, there's no audio input, there's no drive, it's switched off, there's no current flowing through the transistor. Now wattage equals voltage times current. Okay. So when it's switched off, effectively you've got 12 volts on this end, and via the speaker to ground you effectively got 0 volts on this end, because this is a low resistance, maybe 4 ohms. So the voltage across your transistor is 12 volts, but the current is 0. So 12 times 0, 12 volts times 0 amps equals 0. So basically when the transistor is off, the wattage is 0, 0 watts. And that makes sense, that's kind of intuitive. It's not passing any current, there's no wattage. What happens when the transistor is fully turned on? Well, when it's fully turned on, the emitter is basically shorted to the collector. The resistance collector to emitter is very low, maybe 0.1 of a volt, 0.1, 0.2, something like that, yeah? So all the voltage appears across the speaker. So at this point, you've got 12 volts across your speaker to ground. If we'll use 12 volts again, okay? But you've got almost no voltage across the transistor. So where's the wattage being dissipated? Well, the transistor now has almost 0 volts, but it has a little bit. Let's call it 0.1 of a volt. And the current, what's the current? Well, this is a 12 volt supply and your speaker is 4 ohms. So Ohm's law says if this was short, that the maximum current can flow is 3 amps. So Ohm's law says I equals V over R, which is 12 over 4, which is 3. 3 4s and 12. So the current flowing is 3 amps. What's the wattage dissipated by the transistor? 0.1 times 3, which is like 0.3 watts. Okay. So when the transistor is fully turned on, the wattage dissipated by it is very low. The closer this is to 0, the closer the wattage is to 0. All the wattage is actually being now dissipated by your speaker, which is 3 times 12 equals 36 watts. If we're talking DC, okay, which we are at the moment. So that's what you have. So in both cases, when the transistor is on or the transistor is off, the wattage dissipated is basically 0. What happens when it's half on and half off? Well, now effectively we have 6 volts here, okay, whichever one, plus or minus, it's still 6 whether it's positive or negative, okay. This applies to either positive or negative, apart from you can't have minus watts, okay. So when it's half on and half off, you've got 6 volts across the transistor, then you've got 6 volts across the speaker. Yeah, the resistance of the two is the same, 4 ohms, 4 ohms. It's a voltage divider. So we've now got 6 volts across our speaker, okay? What's the current flowing? Well, it's half of what it was when it was 12, yeah? You can do the maths again. 6 over 4 equals 1.5 amps. Okay, so there's now 1.5 amps flowing through our transistor. What's the voltage across the transistor? 6. So the wattage now is 6 volts times 1.5 amps equals 9 watts. Yeah? You can see that. And the other 9 watts, by the way, is being dissipated by the speaker, if it's DC. So this is why the transistors get hot in an amplifier. This is why they have to have heat sinks on them. Okay, the voltage is always changing, the wattage is always changing. But on average, your transistors are probably dissipating half the wattage of the speaker. Yeah, or half of it each, if you like, because they're on off the time each. So a quarter there, and half of it there. But they're all going to be on the same heat sink, so at the end of the day, half the wattage is going into the heat sink. Now, this problem only becomes worse if you decrease the resistance of the speaker to 2 ohms, you double the current, you double the wattage. If you increase the voltage here to a higher voltage, say 24 and minus 24, you're doubling the voltage, you're doubling the wattage again, okay? So this situation of wasted heat will increase with the wattage. You can put more transistors in parallel, like I showed you, and bigger heat sinks and cooling fans, but you're wasting a lot of power. So you might think, well, why not keep the voltage down? Yeah, keep the voltage down. Well, this comes down to the maximum wattage that the speaker can produce. Yeah. So with the 12 volt supply I showed you, even when the transistors are fully on, in DC the maximum wattage is about 36 watts. Yes, there's a RMS formula, but the maths don't matter. You can only get a certain wattage out of a speaker with a plus and minus 12 volt supply. If you want more, you either have to reduce the resistance of the speaker or you have to increase the voltage. You can only reduce the resistance of the speaker so far, so at the end of the day, the only practical way to get more wattage out is to increase the voltage. And as I've just shown you, increasing the voltage increases the power, the wattage dissipated by the transistors, and the hotter it runs. So this is where, and I know there's a bit of theory there, but this is where your Class G and Class H amplifiers come in. So this is a Class G amplifier. We have the same setup, the Class AB. The amplification is the same, it's working the same as this was working. And typically this is used on high powered amplifiers. So when you get into the hundreds of watts up to the kilowatt and so, this is where you use these sort of circuits. So typically for an amplifier of this sort of power, you need a supply voltage, maybe of plus and minus 80 volts, plus and minus 90 volts. But because of the high supply voltage, it dissipates a lot of heat. So you have to make very big, heavy amplifiers. To get around that, what they normally do is they use a lower voltage. So for instance, this is quite typical. Plus 48 and minus 48 volts supply, okay? And your speaker's connected to ground. So the waveform effectively on here can go peak to peak plus or minus 48, yeah? Which is like 96 volts, okay? Peak to peak. What they then have is another voltage rail at double this one. So you'll have a 96 volt positive and you'll have a 96 volt negative supply. And here they fit transistors or MOSFETs. And these could be MOSFETs. But we'll use transistors, why not? Quite typically these use MOSFETs here and transistors here, I will say. So basically we have a transistor that's effectively wired here. And we have another transistor that's effectively wired here. NPN, PNP. And this transistor can basically supply the higher voltage. So the circuit effectively monitors the amplitude of the signal. And when the amplitude is low, it's just using the 48 volt supplies, okay? Your sine waves here. If the sine wave gets to the point where it's going to go above 48s on the peak, yeah, it turns on these transistors and then gives you twice the voltage to the transistor. So now you can go up to 96 volts, just about. And the same on the negative. And when you get to quieter passages of music again, it goes down. And this can work very quickly. I mean, normally the big peaks are on like the bass thumps, the boom, boom, boom of their music, yeah, especially the good stuff they play. So these are switching on and switching off as and when they need it. And that increases the efficiency again. And it means you can make an amplifier with smaller heat sinks, less weight. The disadvantage is that it's more circuitry. You've now effectively got 4 devices fit on the output, and again there may be more of them in parallel. So like I showed you previously, you may have like